Sales and Marketing at TXRX. Welcome to our webinar series. This webinar, which is about land mobile radio transmit infrastructure, is our 7th webinar this year. The webinar will be 45 minutes. You will be muted, so please enter your questions in the question box, and we will address those at the end of the webinar. Actually, the webinar itself, the presentation, will be about a half hour, and then we'll have 15 minutes for Q&A. Now I'd like to introduce our presenter, Jason Wesolowski. Jason is a mechanical engineer and is our quality manager. Also on the call is Jim Grotke, one of our applications engineers, who design our RF conditioning solutions. Jason, please take it away.
All right, well, thank you, Mike. Good morning. As Mike Ryan said, my name is Jason Wesolowski. I'm the QA engineer here at TXRX. My background is in mechanical engineering, but I've been learning a lot about RF myself lately. So bear with me, and hopefully this will be a great webinar for everyone. So going through our agenda today, we're going to start with a brief overview of TXRX. Then we're going to get into the building blocks of the land mobile radio system, moving into the combiner, the antennas, and then at the end we're going to have a discussion about intermodulation. So who is TXRX? Well, we're the industry leader in this area. We were founded in 1976. We hold the original patents on both the combiners and the TTA systems. We're known for our customization and versatility. Those of you who have worked with us before know that we have a dedicated applications engineering team. We use proprietary design software to make sure that you get the quotes that you need with the specific systems that you need. We have the ability to mix and match different systems, different components within those systems to get us the best system for your optimal performance. And we're known for our quality and reliability. We were recently, well, I should say about 3 years ago, we were ISO 9001 certified. We have less than a 0.1% warranty return rate. Our typical lead time is about 4 to 5 weeks, and we're 95% on time with that. But enough about us. Let's talk about the land mobile radio system. So starting off, we have your basic repeater site setup. If you remember, this is generally just a loop, starting with and ending with the subscribers. Subscribers talk on their radios, it's picked up by the by the receive antenna, then down to the tower top amplifier through the multi-coupler to your radio system. That radio then retransmits through the combiner, back up to the TX antenna, and then back out to the subscribers. It's a nice closed loop. Today, though, we're going to be focusing on the red path here, this setup from the radios through the combiner through the antenna. So what's the purpose of a combiner? In a lot of cases, you're going to have multiple radios, and we need to pump those radios through one feed line and one antenna. The reason why we want to do this is because the more antennas you have, the more cost and the more complicated your site's going to be. And it's a lot harder to work on those when they're up on the tower. We can do the combining on the ground, though. We have a couple considerations, though. First, we want to reduce our sideband noise. This will protect your receive signals. Second, we want to minimize or eliminate any intermodulation from the mixing of transmit signals. Anytime you get interference, be it on your receive side or your transmit side, that's a problem. We want to avoid that entirely. But before we can really understand the combiner as a whole, we need to talk about a single channel. So let's look at a typical filter arrangement. In this case, we start with an isolator to make sure that the TX signal goes in one direction and one direction only. This will protect your radios from any power coming back down the line. The second thing we've got is we've got cavity filters, and these condition the signal. You can put them in a series of filters. You can have just one or two, or you can have half a dozen in series. Each filter is going to add to your insertion losses, though. So the more filters you have, the more losses you're going to have in your system. Now, these filters can either be cans, which is our typical, or they can be milled filters if you've got a very specific frequency that you know that you're working with. As we mentioned before, the main goal is to improve the sideband noise and protect the adjacent channels. As long as you can do that, then your system should work for just about every frequency that you might want. So let's talk a little bit more about that and why filters are so important. All signals have bandwidth, and the outgoing signal is usually much stronger than the incoming signal. So that presents us a problem here. And that problem is that we want to protect these receive signals, while at the same time still being able to send out this transmit signal. But you can see this sideband here is going to cause us some interference. So we want to eliminate that. To do that, we're going to use a filter. We're going to restrict the signal in red while protecting the signal in blue. And you add the filter, and it changes the nature of the sideband, knocking it down. Now, with the filter in place, you can see that our transmit and receive signals are clearly separated from each other. You've got no interference on the receive side, and you've got your transmit signal well contained. This is an ideal situation. So let's talk about the filters themselves for a few moments. RF filtering is generally performed with different types of cavities. Most of these are going to be in some sort of can type of arrangement, but you could also be a milled filter. We're going to talk about the canned filters first. The cavities will pass the wanted frequencies with some losses. They will also block the unwanted frequencies. You'll have different cavity lengths depending on the band, and you'll have different diameters depending on your performance. Your diameters can also affect just how much loss you're going to have in your system. All of our cavities will feature a central tuning rod that we can adjust to a given frequency. And along with this, they have a temperature compensation mechanism. The more power you pump through a filter, the hotter the filter gets. You need to be able to deal with that temperature change. So, what type of cavities do we've got? Well, the first is a bandpass. The bandpass passes one frequency and rejects everything else. Second, you have a series notch. The series notch rejects one frequency, but passes everything else. The third one that we've got is what we call a Vari-Notch. This will pass one frequency, reject a second frequency very strongly, and reject everything else to a lesser extent. You'll notice, though, these are all the same basic cans. The only difference is what we call these loops. The bandpass, the series notch, and the Vari-Notch have different loops inside of them. Otherwise, the hardware is mostly the same. So let's talk about each one of these in a little bit more detail. Your bandpass cavity, as we mentioned, is going to pass a specific frequency and reject everything else. You've got two loops, and you can change the orientation of these loops to give a sharper response. Now, if you hook this up to your analyzer, you'll see a curve very similar to what I've got on the left here, with this being your passed frequency and your rejection goes down the sides. By changing the orientation of the loops, you can make these rejection slopes much steeper. So now we've got the bandpass. Let's take a look at the series notch. It's the same concept, but kind of mirror imaged. We have a single frequency that we are rejecting, and everything else is passing. Again, we can change the orientation of the loops to change the response. We also have an additional capacitor directly on the loop to give us a little bit of a fine tuning on it. The Third one we mentioned was the Vari-Notch cavities. These are going to pass a desired frequency, reject most other frequencies, and strongly reject a specific non-desired frequency. In this case, the desired pass frequency can be on either side of the non-desired rejection frequency. And you'll see that I've got on the left, we've got one where the pass is higher than the rejection. We've got one where the pass is lower than the rejection. The reject notches are usually fairly wide though, and they have a second untuned notch on the other side of the pass band. So even though you've got a pass band that's passing higher than the rejection, you're also going to have another untuned rejection notch on the other side here. There's a fourth cavity that we should discuss in particular with combiners, and these are T-Pass cavities. And T-Pass cavity is a special variant used in T-PassCombiners. They behave like a bandpass cavity, and in fact, if you take a look, you'll even see that bandpass loop on this drawing right here. But they also have a second special loop that's designed to connect it to the combiner chain. And that loop looks like this. Otherwise, it behaves exactly the same as a bandpass cavity. We mentioned milled filters before. Milled filters are a filter that can be machined out of a block of metal instead of using the cans. They're usually set to a specific frequency range using fixed internal resonators. Now, the good thing about this is that these can give you a very sharp response, better than canned filters. They have few internal connection points. Great for high power, they tend to have very good reliability. The problem with them, though, is that in addition to taking a long time to actually manufacture, these are a dedicated design. Once you set a milled filter to a specific frequency, it's set there for life. It is very difficult to actually retune a milled filter. As a result of this, if you know that your frequencies will never be changing, milled filters might be okay. But if you think that you might have to change a frequency at some point, you're going to want to go with the standard cans. So we've covered the filters in pretty good time. Let's talk about the combiners themselves. And we've got three main types of combiners. We're going to go over a T-Pass, a hybrid, and a star junction. So let's start with that T-Pass. That's good because I just mentioned that on the filters. T-Pass combiners are the industry standard. We've been using these since we started back in 1976. You can put multiple channels through a single transmission line, and each of these channels are connected up in series. T-Pass cavities will pass a frequency with a short circuit attached to one port on the loop. So, looking at the diagram on the right, we have three T-Pass cavities set up. You'll notice there's a short circuit here at the bottom. These combiners have frequency-specific cabling, which has to be a multiple of half the wavelength in order to move this short circuit up the stack. So whatever your wavelength is, half the wavelength has to be the total length. The total power up to the antenna is going to be the sum of each channel with losses factored in. This means that if you've got one channel that's putting a lot of power through, the other two channels not so much, the total power is going to be the sum with your losses. So, looking at a typical T-Pass arrangement, each channel of a T-Pass combiner is for one transmit signal. These are modular designs, and new channels can be easily added. I mentioned this short circuit at the bottom. Let's say we wanted to add another channel. We can remove this short, put another cable on, and another filter chain, and then just put the short circuit at the bottom of that. Each channel has its own isolator. We use dual junction for traditional radios, but newer radios can get away with a single junction isolator because they have some built-in protections. Remember, these isolators are designed to stop power from coming back and hammering your radios. Each channel can also have as many cavity filters as you need to get the filtering for each specific frequency. And you'll notice on this diagram that we've got 3 channels. The first channel, we've got a Vari-Notch, a series notch, a bandpass, and a T-pass. Same with the second channel. But the third channel, we've only got a bandpass. You can combine these in as many orders, as many configurations as what you need to get the frequency protection that you need. We mentioned the T-pass cavities at the end of each channel in order to bridge the channel to the chain and bring it up to the tower. Oftentimes, there'll also be power monitors on the isolators. There's also a power monitor option at the antenna port to measure your total through and reflected power levels. So this is the drawing for what it looks like on the engineering schematic. What does this actually look like when you build it? Well, here's a typical example of one. In this case, we've got an 84-inch tall rack. This rack has about 12 cavities on it. And you can see that we've got the isolators on the bottom section here. It looks like we also have a pair of milled filters at the top and probably looks like a deck for the receive side. This is a typical illustration, but it's not necessarily going to be what your system looks like. We've got the ability to reconfigure it based on whatever rack you need, whatever size that you need. If you need multiple racks because you've got a particularly complicated system, we can do that. So what are the good and bad parts of a T-Pass combiner? Good thing, we've got less insertion loss than any sort of hybrid system. We can add channels anytime we want. We're easily expandable, easily retuned, easily reconfigured. This is good if you've got customers that start off small and then decide they want to add channels later. We can handle all of that. What are the downsides to this? Well, the first is that your insertion loss increases as your channels and frequencies get closer together. Remember that insertion loss means you need more power to pump through to that transmit. So the closer your frequencies, the more loss you're going to have and the more filtering you're going to need on each frequency. The other disadvantage is that there's a minimum frequency separation. If the frequencies get too close together, a T-Pass combiner just won't handle it. This is going to be based on whatever bands that you're in and whatever cavity size you're dealing with. But it's good to keep in mind. The second type of combiner is something we just mentioned, which is a hybrid. Hybrids use couplers to combine multiple radios onto a single line. The good thing about these is they can be used in situations where the frequency spacing is just too tight for a normal T-Pass combiner. They're very compact and they're broadband, so they can do a lot of different frequencies. The disadvantage is that there's no filtering in the hybrid coupler. So you're going to have some sort of filtering in addition to the coupler. Hybrids also have very high insertion loss relative to a T-Pass combiner. And all that power that you're losing is dissipated as heat. High loss also means less coverage range. So if you've got somebody that needs a lot of range, a hybrid probably isn't going to help with that. Here we have a typical hybrid situation here. We've got 3 channels, they're all fairly close together. We want to combine them through one antenna. So in the case of the first 2, they combine the first hybrid, and then those are combined with the second hybrid. Now I mentioned that there's no filtering inherent in the hybrids, which is why we have a post filter section here. Something to keep in mind is that you have to keep your hybrids balanced as far as your losses. And you can see that in this diagram, where the first connector, you've got 3 dB of loss for each channel. In order to keep that balanced, when we go through the second coupler, we're going to add 1.8 dB to the first 2 channels to get 4.8. And then the second one comes in straight with a 4.8 loss. Now we can keep adding channels, but the more channels you add, the more losses you're going to have. As we mentioned before, we still need this post filter too. So anything that you're losing in the post filter is in addition to anything you're losing in the hybrids. Third combiner is a star junction combiner. And these are fairly similar to the T-Pass, except that you're putting all the channels into a single point rather than connecting them one after another. The cable lengths are based on an average frequency rather than being frequency specific. And they're really mostly usable in the UHF 700 and 800 bands. If you're going to use them in the 700 megahertz bands, you're going to need more bandpass filters on top of that. We still recommend additional filters on the UHF frequencies, in particular because of intermodulation problems on UHF. We'll get to intermodulation a little bit later. So let's say you're shopping for a filter, or for a combiner, I should say, and you're looking at a spec sheet. Well, this is a typical spec sheet that we would have. In this spec sheet, you're going to have the frequency range, what type of cavities you're going to have. This one is using 10-inch cavities, so they're fairly large. Your maximum isolator power, your isolator loads, whatever your minimum TX separation is. Remember that we said that these filters have a minimum separation between the frequencies. Your typical isolation, your input impedance, input loss, temperature range, what type of connectors it uses, what type of mounting it uses, and other options that are available to you. Now, I mentioned that the closer that you get in terms of your frequencies, the more losses you're going to have. Here we can see this in this little chart here on the bottom left. At 1 megahertz separation between frequencies, we're only losing about a dB, and we can pump 250 watts of power through it. Now, the more channels we have, the more losses we're going to have, which is what you see here to the right side of this chart. Something to note, though, is that when we go to only about 150 kilohertz separation, now our losses have jumped up to 1.5 dB, and our maximum power is dropped. And as we get closer, now at 110, now our losses are at 2 dB, and our max power has dropped again. We need to keep in mind that the closer these get, the more losses and the less power you're going to be able to use. So now that we've discussed the 3 different types of combiners, you might have a question of just how complicated can we get? And this picture on the right shows a really good example of that. This is a massive combining system that we built for a customer that has multiple racks, multiple 10-inch cavities on each rack. You can see that there's some isolators on some of these cavities. Each time you see an isolator, it's a different frequency. The point of this, though, is that we can have as many channels as you want. We just need to know how many, the spacing between the channels, and importantly, the physical limitations of the site that you're working on. As you can see from this picture to the right, some of these systems get pretty big. So if space is a limitation, we need to know about that so we can meet that limitation. Now, along with these combiners, there's a special filtering system called a duplexer. Duplexer lets you use the transmit and receive signals through the same antenna. Great, we've reduced the number of antennas even more. This is good when you've only got 1 or 2 transmit and receive signals. It provides good isolation between your transmit and receive. It's got a good power rating. The problem with it, though, is that the more signals you're trying to get, the less likely a duplexer is going to work for you. Remember that each signal has to be individually isolated so it doesn't interfere with anything else. When you've only got 1 or 2 channels, great. When you've got half a dozen, not so much. The next portion we're going to be talking about is antennas, and we've actually got a couple pictured here. So for these antennas, each antenna is going to have a radiation pattern. And we start with what looks like on the left side, which is an ideal pattern. Generally, in an ideal situation, your antenna radiation is going to be shaped kind of like a donut, with the antenna pointing straight through that hole in the middle. When you look at it from the side, you get these lobes here. And this is kind of like taking a cross section of the donut. This is a particularly lumpy donut. But if you look at it from the top, here is where you see that nice round radiation from the center point. Thinking of this as a donut's a pretty good way of thinking. Now, it's important to know that antennas do not create power. They can only direct it. And the vertical elevation and beam width is going to reduce as the antenna gain, which is the directional portion, increases. So at a 0 dB antenna, 0 dBd I should say, you're going to have a fairly fat donut. And as you try to push that direction, you want to transmit further and further, you're flattening out the donut. So here you've got a 3 dBd, and here's a 6. You flattened it out, so you're getting a lot more range, but you're not getting the same vertical distances on it. Usually, this isn't going to be a problem, but you're also going to have losses as you try to direct that signal. So here's more of what it really looks like instead of an ideal situation. On the left, you can see a basic unity dipole antenna, pretty consistent lobes. This is fairly close to that ideal donut that I mentioned earlier. On the right, we have a 10 dB collinear array. They're trying to pump this signal as far as they can. And they've flattened it out, and you'll notice that there's all these extra little lobes on it. So this is what you're going to have to think about when you're doing your antennas. Now, antennas, you can put multiple elements into a single tube. Each element has 30 dB or more isolation between the elements. The elements tend to be passively intermodulation rated, and they have a peak instantaneous power rating. Some models also have a built-in down tilt angle. Now, why would you need that? Well, let's say that your system is on a mountaintop somewhere, and you need coverage in the valleys around the mountaintop. And remember that as we squished that donut, we don't get as much vertical coverage. Well, we can angle those elements downwards so they can hit that valley a lot better. It's also important that we have isolation between your antennas. Your best place for an antenna is going to be at the top of the tower, but you might not be able to do that. More commonly, especially on shared sites, you'll have to have antennas on the sides of the tower. In this situation, vertical separation is better than horizontal separation. The reason for this is proper antenna placement can achieve free isolation. And if they're vertically separated, those two donuts that I mentioned aren't interfering with each other nearly as much. If they're horizontally separated, shadows, and you're going to have some interference issues. That free isolation by having them vertically separated means less filtering that you need in your system. That means a smaller system. The other thing is to get the antenna as far away from any other material. The last thing you want to do is put one of your antennas right next to a giant microwave dish. It's going to cause a shadow. It's going to cause interference. It's going to be problems for your site. We need to make sure that we stay away from any other obstructions. This includes the tower itself as best we can. I mentioned microwave dishes, other antennas, anything else that might be in the way. If you're in a cluttered urban environment, this could include features of local buildings you're trying to stay away from. If your antenna is halfway up a building, you're probably going to need a second antenna on the other side of the building. You have to know your environment in this case. So we've mentioned a word a few times now, and that's intermodulation. So let's talk about that. Intermodulation is the result of mixing two or more signals. You can get some passive intermodulation, but you can also get active intermodulation. These can be incredibly destructive to what you're trying to achieve. Intermodulation can create false signals that can interfere with other parts of your system. Some common mixing points, your final amplifiers on the transmit side is a common point. Multi-couplers, even a rusty bolt is a mixing point for intermodulation. So we need to take some of that into account. Now, intermodulation is kind of a risk-based type of situation. And those of you that work with a lot of firemen might recognize this. This is our fire triangle. In order to have a fire, you need air, heat, and fuel. Only by having all three of them together would you get the fire. Well, intermodulation works the same way. We've got the probability, the RF level, which is how much power you're putting out, and your mixing points. If you can reduce any one of these three legs, you reduce the chance for an intermodulation problem. So what are these three legs? Well, probability is the likelihood of two radios operating at the same time. If you've only got one or two radios at a site, you're most likely not going to see that much. But if you've got maybe 10 radios at the site, you're going to have a pretty good probability that you're going to have multiple radios. The RF level is quite simple. It's the signal strength. The more signal strength, the more likely it's going to mix with something else. And then finally, the mixing point is the places where the signals meet. These are those connections I mentioned earlier, those rusty bolts, dissimilar metals, cable connections, your amplifiers. This is probably one of the easier ones to deal with because you can tell where the mixing points are going to be. Intermodulation products, which is the result of two frequencies mixing, are classified by the order. The order is the sum of the signal coefficients. So if you've got two signals, A and B, you add them together, that's a second order product. If you have three signals, A, B, and C, combining together, you get a third order product. You also get a third order at 2A and B combined together. You can get more complicated. You get 3A, 2B, that's a fifth order. 5A, 4B is a ninth order. Now, the lower the order, the stronger these products are going to be. So a third order product is going to be much stronger than a fifth, and that's going to be stronger than a ninth. As a result of this, these third order, these low number order products are the ones that we're really wanting to control. Now, something to consider is that even ordered products will fall outside of your band, so you don't have to worry about them nearly as much. In this case, we've got an A and a B, an A minus B. You add the two signals together, you're well outside of your fundamentals. You don't have to worry about it. Might cause a headache for someone else, but it's not you. odd ordered products, on the other hand, you've got 2A minus B, 3A minus 2B. If you'll notice, these are right in the middle of your frequencies. So these have to be controlled. So let's see a good example of this. In this case, we've got two radios. The first radio, they've got set to channel 3, and it's got its frequency. Second radio is set to channel 1, it's got its frequency. And when you combine those two, you get this new frequency, which happens to be, in this customer's case, channel 5. Well, what that means is if two people are talking on the first two radios, the guy on the third radio might not hear what he needs to hear. This is why we have to control it. Now, we mentioned probability. Because of the probability and because third order, which is your lowest order in this case, is going to be the most problematic, we do not do third order IM situations. We will recommend that you control it. If you've got frequencies that cause a third order hit, we're going to tell you right away that this isn't good. We can allow fifth order and seventh order, but we need to make sure that we control them appropriately. Again, third order, not allowed. So when we get talking to you as a customer, the first thing we're going to ask you for is what your frequencies are. And this is so we can do an intermodulation study. Doing the study, we're going to compare your frequencies and we're going to generate this report. In this case, we see what our transmit and receive frequencies are. In this customer, they have no third order hits. That's fantastic. They've got no fifth order hits. That's also fantastic. They've got 3 hits at the 7th order. Could be an issue, but probably not. Might be something to kind of keep in mind, though. We can filter for that. Now, we're not considering out-of-band intermodulation because there's no flat mixing point there. So if these, again, if you have an even ordered intermodulation, for example, it's not something you have to worry about. You only have to worry when these frequencies combine into the same range. So we're running short on time. Let's get a quick summary here going on. This is the transmit half of your system. The main goal is to get signals out. You don't want to interfere with your receiving signals. Your combiner is going to put multiple signals onto a single antenna. It's going to protect your receive signals. You have different types of combiners for different applications. And then you have either the TX signals themselves or their byproducts, which can easily overwhelm the RX signals that we have to filter for. So what are some key factors? Well, first is know your system, know your frequencies and how they interact. Know your environment. Are there any other high-level signals in your area? Sometimes you can get interference from someone that's not even on your signal, or not even on your signal plan. It's another customer with another set of subscribers. They just happen to be at the same site. In order to deal with this, we offer a spectrum fingerprinting and noise floor monitoring service. This will tell you everything that's going on at your site. Work with knowledgeable suppliers. The more your supplier knows, the better. To deal with this, we have a questionnaire. Anytime that you contact us wanting us to design a system, we will send you a questionnaire. The more information you can provide on that, the more accurate our design and quote will be, and the better the performance of the system that you're going to get. When we finish all of our work, we're going to give you a design package. Included in this design package, we will have the custom model number of your system, the project and site names, the schematics for both the transmit and receive section, anything electrical or mechanical that you've spec'd out, and the revision history on this design. one last thing to talk about, and that's how to get a hold of us. We've got our website, txrx.com. We've got some dedicated mailboxes, sales at TXRX. We've also got customer service at TXRX if you need anything worked on your system after we sold it to you. And we've got some key personnel. We've got Mike Ryan, who was introduced me earlier. We've got Scott Galligan, the inside sales manager. And of course, there's myself for any warranty and repair type of situations. And with that, I know that I went a little long, so my apologies, but we're going to try to get into the question and answers. And the first question is from Anthony Sparks. It says, for antenna spacing, what is the recommended vertical spacing between TX and RX? What about vertical space from an existing antenna in a different band? Jim, I'm going to kick this one over to you. Jim Grotke is one of our applications engineers, and he has a little bit more experience with this than I am. So I'm going to let Jim answer this one. Go ahead, Jim.
Well, I'll say that the best antenna spacing, we'd like to see a minimum of 10 feet vertical separation tip to bottom. Not center to center, but it should be tip to bottom separation. 10 feet will usually give you pretty good isolation, which will reduce most of the filtering requirements. Some of the other considerations would be your TX to RX guard band. That will also impact how much filtering you need. But as far as antenna spacing, and that would be good with all bands. You'll have higher isolation at a higher frequency plan with that 10 feet spacing, but that would be a good minimum one to shoot for.
Okay, thank you, Jim. Second question is from Mr. Jerry Kessler. How does spectral fingerprinting work? Well, the way that we do this is we actually send a trailer with a set of equipment out to your site. We'll set up an antenna, and we will monitor your site for 24 hours. We are listening to everything that's going on in and around your site. This includes both your own frequencies and everyone else under the sun. Anytime that we hear something, we'll note it. Anytime that we don't hear something, we'll say that you've got a clear band. After 24 hours, we will have this report, which will tell you what other interferences you have. It'll tell you if there's anyone else transmitting with a high-powered system in your area, which may also tell you that you need to filter for that person's system, especially if their system is something that can interfere with your frequencies. We've had this case several times, and the spectrum fingerprinting is something that we definitely recommend if you're in a particularly crowded environment. Anytime that you can get that, that's a good thing. I don't see any other questions coming in. I'll wait a second to see if anyone's typing. But in the meantime, I hope this presentation was beneficial to you. I hope you got some good information out of it. Mike, Jim, if there's anything the two of you would like to say, now's a good time for it.
No, I think that's it, Jason. Thank you.
Okay.
And I think we have one other question that came in. What is the cost for the spectrum fingerprinting? I would recommend, it'll vary depending upon the situation that you're in. So please give us a call or shoot us an email for a quote on that. Okay. And Lee Jones, can we get a copy of this presentation? Yes, I will make that available, a hard copy. In addition, we will have a link to the presentation on our website, and I will email that to everyone. Are there any other questions? We can run over, it's no problem. Here's another question from Wes Hayden. How many channels can be on an antenna with TXRX combined on a duplexer without causing issues? Jim, do you want to address that, or
yeah, Jason? That's definitely a Jim question.
A lot will depend on your frequency plan. We have gone up to 20 hybrid couplers on a duplex system, 20 channels on hybrid couplers, but you're talking massive losses. The the larger number of channels that you put on a duplexer, the larger your losses are going to be. We do 8. I would not recommend any more than, this is me personally, any more than 4 or 5 on a duplexer itself. But that, again, depends all on the particular situation and customer requirements. Hopefully that answers the question.
Thank you, Jim. Are there any other questions? It's certainly okay if we run over, excuse me, if we run over a bit. So I'll give people just a bit more time to ask other questions. Okay. Well, that's it for the Q&A. Again, I'll be sending a link out to the presentation, and we greatly appreciate everybody's time, and I will end the webinar here. Thank you and have a good day.